It starts with a touch so light it barely registers as contact. A forearm brushes a leaf while clearing a narrow trail. Fingers slide along vegetation while harvesting or moving gear. A hand wipes sweat from a neck or cheek after hours in heat that never fully releases its grip. The leaf looks ordinary, green, intact, unremarkable. Then the burn begins, faint at first, like heat trapped under skin. Seconds pass, and the sensation grows sharper, spreading outward in slow, insistent waves. This is not the immediate sting of a wasp or the clean puncture of a spine. This is something that embeds itself, something that stays. Venomous caterpillars do not attack. They do not strike or chase. Their danger is passive, structural, built into the very surface of their bodies. Many tropical species are covered in dense fields of urticating spines or hairs, microscopic, brittle structures designed to detach on contact. Each one is a tiny needle, barbed or hollow, often tipped or coated with toxins. When skin brushes against them, they break free and lodge themselves into the outer layers of tissue, creating hundreds or thousands of micro-injuries in a single motion. The caterpillar does not need to react. The defense triggers automatically, without movement, without intent. From an evolutionary perspective, this strategy is brutally efficient. Caterpillars are soft-bodied, slow, and highly visible. They cannot outrun predators or fight them off. Instead, they turn their own bodies into hazards, surfaces that punish contact. Birds that attempt to peck them learn quickly. Small mammals recoil after a single bite. Even insects that try to grasp them are driven away by pain and irritation. The caterpillar survives not by escaping, but by making itself intolerable to handle. In ecosystems where predation pressure is constant, this shift from active defense to contact deterrence is enough to tip the balance toward survival. In humans, the experience unfolds over time rather than all at once. The initial burn comes from mechanical damage as spines penetrate the skin, triggering pain receptors and inflammatory pathways. Almost immediately, chemical irritation follows. Toxins associated with the spines provoke immune responses, causing redness, swelling, and heat. Histamine release amplifies itching, while localized inflammation increases blood flow to the area. The skin tightens. The sensation deepens. What makes this process particularly insidious is that the spines remain embedded. Unlike venom injected and then metabolized, these microneedles persist, continuing to irritate tissue with every movement. This persistence creates the illusion that the burn is eating its way across the skin. In reality, the damage is static, but the body's response is dynamic. As inflammation ramps up, surrounding tissue becomes more sensitive. Scratching, an almost unavoidable response to itching, drives spines deeper and spreads them to adjacent areas. Fingertips pick up loose hairs and redeposit them elsewhere, extending the affected zone. Sweat and friction redistribute spines along folds of skin, into clothing seams, onto towels or gear. The injury becomes less about the original contact and more about the chain reaction that follows. In the humid jungle, this reaction is intensified. Moisture softens skin, making it easier for spines to penetrate and harder for them to be dislodged. Heat increases circulation, accelerating inflammatory processes. Clothing sticks, rubbing spines back and forth against tissue. There is no clean break between exposure and aftermath. The environment sustains the injury, prolonging discomfort and complicating recovery. What might be a short-lived irritation in a dry, controlled setting becomes a lingering problem when heat, humidity, and constant movement keep the skin in a state of agitation. Venomous caterpillars are not rare anomalies. They are integral parts of tropical ecosystems, feeding on leaves that many other herbivores cannot tolerate. Some specialize on plants with chemical defenses, sequestering toxins and incorporating them into their own protective arsenal. Their bright colors or exaggerated textures are not invitations but warnings, signals to predators that handling comes at a cost. Others rely on camouflage, blending into foliage so perfectly that contact occurs before recognition. In both cases, the defense works only when something touches them. The caterpillar's survival strategy assumes mistakes will happen. Human activity creates those mistakes routinely. Clearing trails pushes hands and arms into dense vegetation where caterpillars feed. Harvesting crops or forest products brings people into contact with leaves that are otherwise ignored by large animals. Wiping sweat is a reflex in hot environments, often done without looking, transferring spines from hands to face or neck. Even resting against trees or sitting on logs can bring skin into contact with caterpillars that move little and rely on stillness for safety. These are not reckless actions. They are normal behaviors intersecting with an organism evolved to turn contact into consequence. There is a deeper ecological logic behind the caterpillar's weaponry. Unlike venomous predators that must balance toxin production with metabolic cost, urticating spines are relatively cheap to maintain. They grow as part of the body surface and can be replaced through molting. Their effectiveness scales with density rather than potency. A single spine may cause minor irritation. Hundreds act as a distributed weapon system. This redundancy ensures that even partial contact delivers a deterrent. Predators learn avoidance not through fatal encounters, but through repeated discomfort, an efficient way to shape behavior without escalating lethality. For humans, the lesson is similar, but harder to internalize. The injury feels disproportionate because there is no clear antagonist, no dramatic moment of attack. The caterpillar may not even be seen. The pain emerges after the fact, growing rather than fading, challenging the assumption that danger announces itself loudly. This mismatch between expectation and experience fuels poor responses. People scratch. They rub. They ignore early symptoms, assuming irritation will resolve on its own. In doing so, they reinforce the very mechanisms that sustain the injury. In rare cases, certain species produce reactions that go beyond localized irritation, triggering systemic symptoms such as nausea, headaches, or changes in blood clotting. These effects are not universal, but they underscore the diversity of chemical defenses evolved by caterpillars across different lineages. Each represents a solution to the same problem: how to survive long enough to feed, grow, and metamorphose in a world full of mouths. The adult forms, moths and butterflies, may be fragile and short-lived, but the larval stage must endure weeks of exposure. Defense at this stage is not optional. From a broader biological perspective, venomous caterpillars highlight an often overlooked principle. Not all harmful interactions involve active aggression. Some are the byproducts of structural design meeting sensitive tissue. The caterpillar does not escalate or pursue. The harm arises from persistence, spines that stay put, toxins that continue to irritate, and behaviors that amplify exposure. The forest rewards such strategies because they conserve energy and reduce risk. For humans, adapting means recognizing that avoidance, not reaction, is the most effective defense. Understanding these insects requires shifting focus from the moment of contact to the system that follows. The caterpillar is one component. The skin's immune response is another. Climate, behavior, and time complete the picture. The burn keeps growing, not because the animal is doing more, but because the body is responding exactly as it evolved to, escalating inflammation in the face of persistent irritation. In this way, the injury is co-created, shaped by both organism and environment. Venomous caterpillars do not inspire fear through size or speed. They teach through consequence. They occupy the quiet space between hazard and habitat, reminding us that in dense ecosystems, danger is often passive and proximity-based. A leaf is never just a leaf. A brush of skin is never just a brush. The forest does not need to reach out to harm you. Sometimes it only needs you to reach in. The countdown does not begin with pain. It begins with silence. In the dim margin between night and shelter, under a corrugated roof, inside a thatch gap, along a beam warmed by the day's heat, bats move with a restraint that makes them easy to forget. They are not crawling across skin or announcing themselves with threat displays. They drop, glide, brush past, and vanish. When contact happens, it is often incidental, brief, and almost undetectable. A pinprick on exposed skin. A faint scratch mistaken for a thorn or splinter. A moment of pressure that fades as quickly as it appeared. Nothing about the sensation demands urgency. That is the problem. Bats are built to interact with bodies without being noticed. Their survival depends on it. Whether feeding on insects mid-air, fruit in canopy shadows, or blood from sleeping mammals, bats operate in sensory spaces where sound, vibration, and touch are minimized. Their teeth are small and sharp, designed to pierce without resistance. Their saliva contains anticoagulants and compounds that reduce irritation, allowing feeding to continue uninterrupted. In many cases, the body does not register the bite as an injury at all. By the time awareness arrives, if it arrives, the interaction is over. This is why bat-related risk is not defined by drama, but by delay. Tiny bites are ignored because they do not feel like injuries. They do not swell immediately. They do not bleed visibly. They do not impair movement. In environments crowded with insects and abrasive vegetation, a mark that does not hurt is dismissed without thought. People wake with a faint line on the skin and assume it came from something mundane. They brush it off, literally and mentally, and move on. The danger is not what happens next. It is what does not happen. Bats occupy a unique ecological position. They are long-lived for their size, highly social, and capable of sustained flight that moves pathogens across landscapes. Their immune systems are adapted to coexist with viruses that would devastate other mammals, tolerating infections without severe illness. This tolerance allows pathogens to persist silently within bat populations. The bats are not sick. They are reservoirs. The viruses they carry remain viable, waiting for opportunities to cross species boundaries. When that crossing happens through a bite or scratch, the clock starts. For certain viral exposures associated with bats, prevention depends entirely on timing. There is a window, often measured in days, sometimes weeks, during which post-exposure intervention can stop infection before it reaches the nervous system. Once that window closes, outcomes become grim. The disease does not announce its progress loudly. Early symptoms resemble common illnesses: fever, fatigue, vague discomfort. By the time neurological signs appear, intervention is no longer effective. At that point, medicine can only support the body as it fails. This is the countdown. It is invisible. It advances regardless of how the bite felt, regardless of how small the wound looked, regardless of how certain someone was that nothing happened. Human behavior aligns disastrously well with this delay. Attic cleanup exposes people to roosts where bats cluster in confined spaces. Disturbed animals may fall, cling, or attempt to escape through narrow gaps, increasing the chance of contact. Handling grounded bats, often out of concern rather than fear, brings hands close to mouths and teeth optimized for penetration. Sleeping in open structures, where walls and ceilings are incomplete, allows bats to pass through living spaces without obstruction. In these scenarios, contact is not aggressive. It is incidental. And incidental contact is the hardest to remember. The ecological context matters. Bats choose roosts that provide stable temperatures and protection from predators. Human structures often replicate these conditions unintentionally. Roof spaces trap heat during the day and release it slowly at night. Gaps under eaves mimic cave entrances. Attics remain undisturbed for long periods, allowing colonies to establish. From a bat's perspective, these are ideal habitats. From a human perspective, they are blind spots, spaces we enter occasionally and assume are inert. Thermoregulation plays a subtle role in exposure. Bats regulate body temperature differently than most mammals, entering torpor to conserve energy and heat. In this state, they are less responsive, more likely to be handled or brushed against inadvertently. When disturbed suddenly, they may bite reflexively, not as an attack, but as a last resort defense. The bite is quick, efficient, and easy to miss. Predator-prey dynamics also shape these interactions. Bats are prey for owls, snakes, and mammals. Their primary defense is evasion, not confrontation. When evasion fails, when cornered in a hand, tangled in netting, or trapped indoors, they use the only tools available. The goal is escape, not injury. The consequence, however, is exposure. The spiral emerges from inaction. Because the bite did not hurt, people do not seek care. Because there is no dramatic wound, there is nothing to clean or dress. Because the bat flew away, the incident feels resolved. Days pass. The window for prevention narrows silently. When symptoms finally prompt concern, the connection to the original contact is often lost. People cannot recall a moment worth mentioning. The opportunity closes without ceremony. This pattern is reinforced by myth. Bats are often framed as either harmless mascots or monstrous threats, with little space for nuance. The reality is less cinematic and more dangerous. Most bats are not aggressive. Most encounters do not result in disease transmission. But the cost of the rare transmission event is extreme, and the only defense is early action based on suspicion rather than certainty. That runs counter to human instinct, which prefers evidence and urgency. From a biological standpoint, the pathogens associated with bats exploit the nervous system because it is difficult for the immune system to clear once infected. The slow progression allows the virus to travel along nerves toward the brain, shielded from many immune responses. This journey takes time. That time is the window. Miss it, and the outcome is largely predetermined. Bats themselves remain unaware of any of this. They continue their nightly routines, emerging at dusk, navigating by echolocation that maps the world in exquisite detail, consuming insects that would otherwise overwhelm ecosystems, pollinating plants, dispersing seeds. Their ecological value is immense. Entire forests depend on them for regeneration and balance. They are not villains in this story. They are participants in a system where unintended consequences arise from proximity. The closing irony is sharp. Bats prevent countless human illnesses by controlling insect populations that spread disease. They sustain ecosystems that buffer climate extremes and support biodiversity. And yet, a single unnoticed bite can carry consequences far more severe than the hazards they help suppress. The same animal that protects human health at scale can threaten it at the individual level through nothing more than a brief, silent interaction. This chapter closes the arc not because bats are the most dramatic danger, but because they embody the central theme. The most dangerous moments are the ones that do not feel dangerous at all. The countdown does not require panic or blood. It requires only neglect. The forest does not always attack outside. Sometimes it moves into ceilings, rafters, and walls. Sometimes it brushes past in the dark and leaves behind nothing you can point to. Survival in these cases depends on respecting uncertainty, treating absence of pain as meaningless, acting on possibility rather than proof. When it comes to bats, waiting is not neutral. Waiting is a decision. And in the quiet space between a tiny, forgettable bite and the moment symptoms finally force recognition, the window closes, unnoticed, irreversible, and absolute. The first wound is easy to forgive. A pinprick on the ankle, a faint itch behind the knee, a soft tickle on the wrist that barely registers against the heat and noise of the forest. There is no blood to speak of, no dramatic injury, no visible threat. You swat, you scratch, you move on. In environments shaped by claws, fangs, and venom, the mosquito feels like background static, annoying but trivial. And that assumption is the trap. Mosquitoes do not announce danger through pain. They erase it. Their mouthparts are engineered not to hurt, but to go unnoticed long enough to feed. A bundle of microscopic needles slides into the skin, guided with precision toward blood vessels, while saliva delivers anticoagulants and mild anesthetics. The goal is not damage. The goal is access. By the time the itch appears, the exchange is already over, and whatever the mosquito carried has been introduced quietly into the bloodstream. This is why the smallest wound can become the biggest curse. The injury itself is meaningless. The consequence is delayed. Mosquitoes are not random attackers. They do not wander blindly through the air hoping to collide with skin. They hunt using layered sensory systems that rival much larger animals in sophistication. Carbon dioxide is the long-range beacon. Every exhale creates an invisible plume that mosquitoes can detect and follow over surprising distances. Heat refines the signal, guiding them toward warm-blooded bodies in a cluttered environment. Odor completes the picture. Human skin releases a complex chemical signature shaped by sweat, bacteria, diet, and genetics. To a mosquito, this signature is as distinctive as a face. Some people are bitten more not because they are unlucky, but because they are louder in chemical terms. Sweat-soaked skin, active muscles producing heat, exposed ankles radiating warmth near ground level, all of these sharpen the signal. Dusk amplifies the effect. As temperatures drop slightly and wind slows, scent plumes stabilize. Mosquitoes emerge from resting sites with their sensory world suddenly clear and navigable. What feels like relief from the day's heat to a human is the beginning of peak hunting conditions for them. Ecologically, mosquitoes are woven into the fabric of these systems. Their larvae develop in standing water, puddles, floodplains, tree holes, slow-moving margins, feeding on microorganisms and organic debris. In doing so, they help process nutrients and support aquatic food webs. Adults become prey for birds, bats, frogs, and insects. They are not anomalies or invaders. They are connectors, linking water, land, and air through their life cycle. But their role as vectors, the ability to move pathogens between hosts, changes the stakes entirely. When a mosquito feeds, it does more than draw blood. It samples the host's internal environment and, if infected, can acquire viruses or parasites that replicate within the mosquito itself. This replication is temperature dependent, accelerating in warm climates where mosquitoes thrive. Days or weeks later, when that mosquito feeds again, the pathogen is delivered directly into the bloodstream of a new host, bypassing many of the body's external defenses. There is no wound to clean, no obvious injury to monitor. The entry point closes almost immediately. This is where the spiral begins. You feel fine today. The bite fades. The itch subsides. Work continues. Travel continues. Hydration lapses. Fatigue accumulates. Then, days later, symptoms appear: fever, aches, headache, malaise, easy to mistake for exhaustion or a mild illness. The delay severs cause from effect. People do not connect how they felt at dusk on a riverbank to how they feel now in a camp, a village, or a city. Treatment is delayed not because care is unavailable, but because urgency never arrives on time. Mosquito-borne diseases exploit this gap. They do not incapacitate immediately, because immediate incapacitation would limit spread. Evolution favors pathogens that keep hosts mobile long enough to be bitten again. The mosquito is not malicious in this arrangement. It is a courier shaped by millions of years of co-evolution between insects, microbes, and vertebrates. Its biology is tuned for efficiency, not harm. The harm emerges from scale, billions of bites across populations, each one insignificant on its own. Human behavior aligns perfectly with mosquito opportunity. Sweat accumulates during physical work, intensifying odor cues. Clothing loosens or comes off as heat builds, exposing ankles, wrists, and necks. Repellent is skipped because it smells, because it ran out, because it feels unnecessary in the moment. Work stretches into dusk because tasks feel unfinished and daylight lingers just long enough to justify staying. By the time mosquitoes peak, people are tired, distracted, and less vigilant. Unlike dramatic predators, mosquitoes do not force immediate decisions. They allow bad decisions to compound quietly. The body's immune response may handle the pathogen efficiently, or it may not. That outcome depends on prior exposure, nutritional status, hydration, stress, and genetics. Variables invisible in the moment of the bite. The mosquito does not discriminate. It samples whoever is available, guided only by signals of breath and heat. From a physiological standpoint, the mosquito's saliva is a marvel of specialization. It prevents clotting, suppresses pain, and modulates immune responses just enough to keep blood flowing. These same properties facilitate pathogen entry by dampening local defenses at the bite site. The body responds later, once the pathogen has already moved beyond that initial interface. By then, The battle has shifted from skin to systems. There is a psychological asymmetry here that makes mosquitoes uniquely dangerous. Humans are wired to respond to immediate threats. Pain demands attention. Visible injury triggers care. Delayed consequences do not. The mosquito bypasses our instincts by operating below the threshold of alarm. It does not need fear or force. It relies on neglect. In the forest, this makes mosquitoes more consistent adversaries than many large animals. You can avoid a snake by watching where you step. You can avoid a caiman by respecting the water's edge. Avoiding mosquitoes requires sustained discipline, covering skin when it is uncomfortable, applying repellent repeatedly, altering work schedules, accepting inconvenience in exchange for invisible protection. These measures feel excessive precisely because the threat does not feel real in the moment. Ecologically, mosquitoes respond quickly to human presence. Camps create pools of standing water. Footprints fill with rain. Containers collect runoff. Body heat and CO2 concentrate in small areas. The mosquito population does not need to grow dramatically to increase risk. It only needs to align with human behavior. This alignment happens naturally, without planning or malice, driven by physics and chemistry. The tragedy of mosquito-borne illness is not that it is mysterious. The mechanisms are well understood. The tragedy is that understanding does not translate into instinct. People learn through stories of dramatic injury, not through statistics of delayed illness. The mosquito exploits this bias perfectly. It leaves no narrative hook, no scar to point to. Only a memory of an itch that seemed unworthy of concern. In this way, mosquitoes invert the logic of danger in the wild. The largest threats are not always the most visible or violent. Sometimes they are the ones that feel like nothing at all. A creature light enough to rest on skin without being felt can alter lives far beyond the moment of contact. The forest does not distinguish between dramatic and mundane hazards. It rewards adaptations that work. Mosquitoes work because they are precise, patient, and pervasive. They do not need to win every encounter. They only need enough of them to succeed often enough. The lesson of mosquitoes is not paranoia, but respect for delay. Protection matters before symptoms appear. Choices made at dusk echo days later. The smallest wound, the one you barely noticed, may be the only one that truly matters. In ecosystems dense with life, danger does not always arrive with force. Sometimes it arrives quietly, rides your breath, tastes your skin, and leaves before you ever realize it was there. The hand goes to the tree the way it always does, without thought, without ceremony. Bark is assumed to be solid, inert, a surface you can trust. Fingers spread, weight shifts, and for a fraction of a second, everything feels normal. Then the bark moves. Not dramatically, not all at once, but in ripples and fragments, as if the tree itself has come alive. What follows is not just pain, it is interruption. A violent, total override of the body's ability to decide what to do next. Bullet ants do not hide underground or wait passively for contact. They live on trunks, vines, and roots, vertical highways of the rainforest where traffic is constant and escape routes are limited. Their size alone is enough to break expectation. These are not background insects. They are heavy-bodied, slow-moving, deliberate, with mandibles built for gripping and stingers evolved for a single purpose, to end confrontation immediately. When disturbed, they do not warn and they do not retreat. They commit. The sting lands with surgical precision. The stinger penetrates deep, anchoring momentarily as venom is delivered directly into muscle and nerve-rich tissue. The chemistry that follows is not random. Bullet ant venom is designed to hijack the nervous system's priorities. Its primary component binds to pain receptors and locks them in the on position, forcing continuous firing. This is not a spike of pain meant to fade. It is a sustained signal that drowns out competing sensory input. Vision narrows. Hearing becomes distant. Thought collapses into sensation. Pain here is not a symptom. It is the weapon. In evolutionary terms, this makes perfect sense. Bullet ants are large, conspicuous, and slow compared to many predators. They cannot rely on speed or invisibility. Instead, they evolved a deterrent so overwhelming that a predator's only viable response is withdrawal. The venom does not need to kill. It needs to break behavior. Any animal that learns this lesson once will not make the same mistake twice. The cost is too high. For humans, the effect is destabilizing in a way few other injuries are. The pain is immediate and absolute, but what follows is more dangerous. Muscles tense involuntarily. Fine motor control degrades. Balance falters. The body heats rapidly as stress hormones flood the system. Nausea builds, not as a secondary reaction, but as part of the same cascade. Pain, stress, and autonomic overload feeding into one another. Hands shake. Knees weaken. Breathing becomes shallow and fast. And this is where the spiral begins. Bullet ants rarely sting alone. They live in colonies, and their nests are often spread across tree bases, roots, and surrounding leaf litter. A hand on a trunk or a foot near a nest entrance can trigger multiple stings in seconds. Each sting compounds the neurological assault. Pain signals stack rather than replace one another, saturating the nervous system. The body struggles to regulate temperature as muscles remain locked in tension. Sweating increases, dehydration accelerates, and judgment erodes further. In this state, people fall, not from dramatic heights, but from standing positions, from logs, from uneven ground. Secondary injuries follow: sprained ankles, cracked ribs, head impacts. The ants are no longer involved, but their venom set the conditions. In the rainforest, where footing is never stable and surfaces are rarely forgiving, losing control of your body for even a minute can cascade into serious harm. Bullet ants are deeply embedded in the ecology of the forest. They are not roaming aggressors. They are territorial defenders and opportunistic foragers, preying on insects and scavenging where necessary. Their presence shapes the behavior of other animals. Many predators avoid trees and vines heavily patrolled by these ants, creating invisible boundaries that influence movement patterns throughout the understory. In this way, bullet ants help structure the spatial dynamics of the forest, enforcing zones of risk through pain rather than physical barriers. Their sensory world is tuned to vibration and chemical cues. A hand pressing into bark sends shockwaves through the substrate. A footstep near a nest compresses soil and leaf litter. These signals are unmistakable. To the ants, they indicate threat, something large, potentially destructive, and too close to tolerate. The response is immediate, because hesitation would mean crushed workers, breached nest chambers, or exposed brood. There is no room for warning rituals when the cost of delay is colony failure. Human encounters tend to occur during moments of fatigue or inattention, leaning on trees while resting, grabbing vines for balance on steep terrain, stepping near roots without scanning the ground. These are not reckless acts, they are survival behaviors in a difficult environment. But they intersect perfectly with the ant's defensive architecture. Bullet ants choose nest sites that maximize protection and access to food, not human safety. Trees, roots, and vines are ideal for them, and unavoidable for us. The venom's most insidious feature is not its intensity, but its duration. Pain can persist for hours, sometimes longer, maintaining muscle tension and stress responses well beyond the initial sting. During this window, the risk of secondary injury remains elevated. People stumble. They misjudge steps. They rush decisions simply to escape the sensation. In the forest, haste is often more dangerous than hesitation. From a physiological standpoint, the venom exposes a vulnerability in human design. Our nervous system prioritizes pain as an immediate survival signal, but it assumes pain will either resolve quickly or coincide with visible injury. Bullet ant venom exploits this assumption by delivering extreme pain without structural damage. The body reacts as if it is being destroyed, even though tissue remains largely intact. Energy is burned. Focus is lost. Thermoregulation struggles to keep up. The system is thrown into crisis mode for a threat that no longer exists. This mismatch between perception and reality is what makes the sting so disabling. The danger is not ongoing, but the body behaves as if it is. In an environment that demands constant awareness and controlled movement, this false alarm is costly. Bullet ants do not need to chase or pursue. Their defense works precisely because it ends interaction immediately. A predator, or human, retreats not because it has been injured, but because it cannot function. This is behavioral dominance achieved through chemistry. It is one of the most efficient deterrent strategies in the animal world, and it explains why these ants can afford to be large, slow, and visible. Understanding bullet ants requires abandoning the idea that pain is merely a byproduct of injury. In this case, pain is the adaptation. It is the point. The forest does not rely solely on claws and teeth to enforce boundaries. Sometimes it uses neurological overload. For people moving through these ecosystems, the lesson is brutal but clear. Trees are not neutral. Vines are not handholds by default. The vertical space of the forest is as defended as the ground beneath it. Bullet ants do not advertise their presence with sound or color. They let pain do the talking, and they speak fluently. The ants are not cruel. They are precise. Their venom is tuned to break decisions, not bodies. The falls, the secondary injuries, the panic, those belong to us. They are the result of a nervous system pushed beyond its design parameters by a weapon evolved specifically to do exactly that. The forest floor is not a surface so much as a layered machine built from pressure, moisture, and decay. Bark sloughs off trunks in curled plates. Rocks settle into the soil as if sinking. Leaves compress into a warm, fibrous mat that breathes faintly with heat and microbial activity. This is where hands go first. When people move through jungle camps or work clearings, they grip bark for balance, roll stones to check footing, lift logs to dry them, or sweep leaf piles aside to make space. These gestures feel safe because they are habitual, learned, far from ecosystems where the ground itself bites back. Under bark and rock, however, the centipede waits, not as an ambush predator in the cinematic sense, but as a compressed system of muscle, venom, and reflex adapted to darkness and touch. The encounter is never announced. There is no warning coloration exposed, no rattle, no hiss. The first signal is pain. Scolopendra does not live on the forest floor. It lives inside it. The flattened body and segmented legs are designed to move through tight seams, under bark plates, between stones, inside termite galleries, and along the undersides of rotting logs where humidity remains high and temperature stable. This is not accidental habitat selection. Centipedes lose water rapidly through their cuticle and rely on moist microclimates to prevent desiccation. By day, they remain hidden in these narrow refuges, conserving water and energy. At night, when temperatures drop and humidity rises, they emerge to hunt insects, spiders, scorpions, and even small vertebrates. Their world is defined by contact, not sight. Antennae sweep constantly, tasting the air and substrate, reading vibrations and chemical cues left by passing prey. In this darkness, reaction time is everything. When a human hand enters that space, the centipede does not interpret it as a hand. It registers pressure, warmth, and sudden enclosure. The response is not aggression, but defense through offense. An evolved reflex honed by millions of years of being crushed, pecked, bitten, and burned by predators far less forgiving than people. The forcipules, modified front legs ending in venom-injecting claws, snap forward with remarkable speed. Unlike a spider or snake that may deliver a single controlled bite, Scolopendra often thrashes. The body coils and uncoils, legs hooking for leverage, the head striking repeatedly as long as contact remains. Each puncture introduces venom deeper into tissue, and the damage compounds rapidly. The venom itself is not designed to kill humans. It is a biochemical toolkit meant to immobilize arthropod prey quickly and deter vertebrates long enough for escape. It contains neurotoxic and cytolytic components that disrupt nerve signaling and damage cell membranes, producing immediate pain, followed by swelling and inflammation. Victims often describe the sensation as a deep, spreading burn, hot, electric, and persistent. This is not surface pain. The forcipules penetrate muscle and connective tissue, delivering venom where inflammatory responses amplify its effects. Blood vessels dilate, fluid leaks into surrounding tissue, and pressure builds. In some cases, lymphatic flow is disrupted, causing swelling to track along limbs rather than remaining localized. The pain does not fade quickly because the venom triggers a cascade rather than a single event. In the jungle, this physiological response interacts dangerously with environment. Heat accelerates circulation, spreading venom effects more rapidly. Humidity prevents wounds from drying, keeping puncture sites open and vulnerable. Sweat and moisture soften skin, reducing its ability to act as a barrier against secondary infection. Scratching, a near universal response to pain and irritation, worsens the situation. Fingernails introduce bacteria from the skin and environment directly into damaged tissue. The swelling restricts movement, encouraging further rubbing and pressure. What begins as a defensive bite spirals into prolonged inflammation, a feedback loop driven not by venom alone, but by climate and behavior. Centipedes evolved for this world. Their venom must act quickly in conditions where prey can escape into burrows or leaf litter within seconds. Their thrashing is adaptive, maximizing contact when predators attempt to pin or crush them. Their nocturnal activity aligns with peak humidity, reducing water loss and increasing sensory effectiveness. Even their segmented bodies contribute to survival. If restrained, the rear half can continue to strike while the front searches for escape. These traits make Scolopendra a successful predator and a formidable defensive organism, not because it seeks conflict, but because hesitation is lethal in its ecological niche. Human encounters often occur during moments of perceived safety. Camp cleanup in the late afternoon, when people believe the most dangerous animals are inactive. Moving logs to dry them or clear space, exposing the cool, damp underside where centipedes rest. Reaching into rock piles to retrieve gear or firewood without visual confirmation. Sleeping low to the ground, where body heat attracts insects and the predators that follow them. In some regions, centipedes are drawn to camps by concentrations of prey, cockroaches, beetles, spiders, creating a quiet overlap between human activity and centipede foraging routes. At night, a wandering individual may explore bedding, clothing, or packs left on the ground, not out of curiosity, but because these objects trap warmth and moisture. The danger is not that centipedes hunt people. They do not. The danger is that their survival strategy leaves no margin for error when contact occurs. A snake may warn. A large mammal may flee. A centipede, compressed against bark or stone, has only one option: strike until the pressure stops. This is why bites often involve multiple punctures clustered in a small area, sometimes in a rough arc that traces the movement of the head as the body thrashes. The resulting tissue damage can be disproportionate to the animal's size, especially in fingers, toes, or joints where swelling quickly limits circulation. From an ecological perspective, Scolopendra plays a stabilizing role in the forest floor community. By preying on insects and other arthropods, it regulates populations that would otherwise explode in warm, resource-rich environments. It competes with spiders and scorpions, filling a niche that rewards speed and venom over web building or ambush. Its presence influences the behavior of prey species, shaping nocturnal movement patterns and microhabitat use. In this sense, the centipede is not an anomaly, but an integral component of the decomposer-predator interface, the zone where plant matter becomes animal biomass. Understanding this context reframes the encounter. The centipede is not a rogue hazard, but a consequence of ecological efficiency meeting human intrusion. The pain it delivers is real, intense, and sometimes medically significant, particularly for children or individuals with compromised immune systems. Yet it is also a signal, an evolutionary message encoded in venom chemistry and reflex, that the space under bark and rock is already occupied. In temperate environments, this message is muted. In the tropics, it is amplified by heat, moisture, and biological density. The lesson is not fear, but precision. Slow movements. Visual confirmation before contact. Elevating sleeping areas. Shaking clothing and gear. Recognizing that the forest floor is not inert, but active, layered with organisms optimized for survival at human skin depth. Scolopendra does not escalate because it cannot afford to. Its world punishes hesitation. When hands go first, the centipede answers with everything it has, not out of malice, but because evolution has taught it that anything large enough to reach into its shelter is large enough to end it. In the end, the centipede's danger lies less in its venom than in its alignment with the jungle itself. Warmth feeds inflammation. Humidity preserves wounds. Darkness removes warning. The animal is only the trigger. The environment completes the reaction. Understanding that chain, animal, physiology, climate, behavior, is what turns an encounter from a mystery into a system. And systems, once seen clearly, can be navigated. On the surface, it looks like nothing. A dull, angular insect flattened against bark, legs tucked close, body broken into quiet lines that echo the cracks and scars of the tree itself. It does not advertise danger. There is no bright warning color, no exaggerated weapon held aloft, no sound. In a forest crowded with stings, fangs, and venomous displays, the assassin bug survives by being visually forgettable. The human eye slides past it without registering threat. Fingers brush bark. A hand steadies itself on a log. Clothing drags against rough wood. Then, without ceremony, the insect stabs. The sensation is immediate and wrong, not the diffuse itch of a mosquito or the fleeting burn of an ant sting, but a sharp, focused penetration that feels too deliberate to be accidental. The proboscis goes in cleanly, driven by muscles designed to pierce armored prey. For the assassin bug, this is not a bite in the mammalian sense. It is a feeding strike. The mouthpart is a rigid, needle-like rostrum evolved to puncture exoskeleton, inject enzymes, and liquefy tissue from the inside. When it enters human skin, the insect does not adjust its chemistry. It delivers the same cocktail it would use on a beetle or caterpillar, saliva rich in digestive enzymes, anticoagulants, and compounds that disrupt local tissue integrity. Assassin bugs are predators, not parasites. They do not sip blood. They kill, dissolve, and drink. Their saliva is external digestion in liquid form, designed to turn solid prey into something drinkable. In insects, this process is efficient and final. In humans, it becomes a localized biochemical assault. The injected saliva begins breaking down cells almost immediately, triggering pain receptors deep in the skin. Blood vessels dilate. Immune cells flood the area. Swelling builds as fluids leak into surrounding tissue. Unlike a venom optimized to spread systemically, assassin bug saliva stays largely confined to the strike zone, which makes the pain feel concentrated and stubborn, an angry knot that refuses to fade. The irony is that the insect never intended escalation. Assassin bugs rely on stealth because their survival depends on not being noticed. Many species actively coat themselves in dust, soil, or debris, masking their outline and scent. Some even collect the carcasses of prey and wear them as camouflage. This behavior is not grotesque ornamentation, but a functional strategy, blending into the background while waiting motionless for hours, sometimes days, until the vibrations of passing prey trigger a strike. Their nervous systems are tuned to micro-movements, the scrape of an insect leg on bark, the tremor of a wing folding. When a human hand replaces an insect body, the sensory cue is similar enough to trigger the same response. What follows after the stab is where the human cost grows. Pain invites attention, and attention invites interference. The wound itches as inflammation develops. The skin tightens as swelling increases, and fingers instinctively scratch. In the humid jungle, skin rarely stays clean or dry. Sweat, dirt, plant resin, and bacteria coat the surface. Fingernails push these contaminants into puncture sites already compromised by enzyme activity. The assassin bug's saliva has softened tissue boundaries, making it easier for microbes to invade. What was initially a localized reaction becomes an inflamed lesion, sometimes expanding over days rather than resolving. This is the spiral. People dismiss the bite because it came from something small and unremarkable. There is no dramatic swelling at first, no systemic symptoms, no immediate disability. The pain lingers, then dulls, then returns as itching. The area is ignored or roughly treated. In remote settings, antiseptics may be unavailable or used sparingly. Heat and humidity slow healing. Secondary infections take advantage of damaged skin and constant moisture. The original strike fades into memory, but the wound grows uglier. Redness deepening, edges hardening, tenderness persisting long after the insect is gone. Assassin bugs thrive in these environments because their physiology matches the forest's rhythms. They are ectothermic, their activity governed by ambient temperature. Warm days and nights keep their muscles responsive and their digestion efficient. They select perches that maximize encounter rates: tree trunks, fallen logs, the undersides of branches, places where insects pass frequently and humans rest without thinking. Sitting on a log during a break, brushing clothing against bark while moving through dense vegetation, handling insects out of curiosity or habit. These are not reckless acts, but they intersect precisely with the assassin bug's hunting strategy. From an ecological perspective, assassin bugs are regulators. They remove herbivorous insects that would otherwise strip leaves and weaken plants. They prey on agricultural pests, indirectly supporting the growth of forests and human crops alike. Their feeding strategy is slow but decisive. Once struck, prey rarely escapes. Enzymes paralyze and dissolve, turning movement into stillness. This efficiency allows assassin bugs to conserve energy in ecosystems where food availability fluctuates and competition is intense. Their presence shapes insect behavior, pushing prey species to alter foraging times and routes, subtly restructuring the forest's invisible traffic patterns. There are moments of unexpected complexity. Some assassin bugs exhibit maternal care, guarding egg clusters against predators. Others engage in chemical mimicry, producing scents that attract specific prey species. Their evolutionary success is not built on brute force, but on precision, anatomical specialization aligned with behavioral restraint. They strike once, feed slowly, and remain still again, trusting camouflage and chemistry to do the rest. Humans, by contrast, are noisy intruders in this system. We lean, brush, swat, and scratch. We move during the day when assassin bugs rest, assuming inactivity means absence. We associate danger with size and spectacle, overlooking organisms whose weapons are hidden and whose damage unfolds over time. The assassin bug exploits this cognitive gap, not intentionally, but inevitably. The pain it causes is instructive. It is a reminder that feeding adaptations do not translate cleanly across species boundaries. Chemistry designed for insects becomes irritation in mammals. Enzymes meant to liquefy tissue for consumption become agents of inflammation when injected into skin that cannot be digested quickly. The body reacts as if under attack because, at a cellular level, it is. Yet the attack is incomplete, leaving behind damaged tissue rather than consumed prey. Healing becomes a negotiation between immune response and environmental stress. In the broader context of jungle hazards, assassin bugs occupy an uncomfortable middle ground. They are not lethal. They do not hunt humans. Their bites rarely make headlines. And yet, they exemplify a category of danger that is easy to underestimate. Organisms whose primary threat lies not in immediate trauma, but in the way small injuries interact with climate, behavior, and neglect. The forest does not need to maim you outright. It only needs to complicate recovery. Understanding assassin bugs means understanding restraint as a survival strategy. Stillness over speed, chemistry over strength, invisibility over intimidation. These traits make them effective predators and accidental antagonists to humans. When people encounter them, the lesson is not paranoia, but awareness. Bark is not empty. Logs are not neutral. Insects are not harmless by default. The assassin bug will never announce itself. It will never chase or pursue. Its danger exists only at the moment of contact, when two systems briefly collide, one optimized for external digestion, the other for rapid healing in conditions that undermine it. The result is disproportionate discomfort from a creature that never meant to be noticed at all. And in that quiet mismatch between intent and outcome, the forest reminds us that survival is not about malice, but alignment. The moment itself often feels survivable. A burst of movement at the river's edge, a sudden weight, a violent grip that lasts seconds instead of the imagined eternity. There is shouting, splashing, a frantic retreat onto mud or sand. Blood is visible, but it flows rather than pours. The limb still moves. The person is alive, upright, breathing. In the immediate aftermath, the story writes itself as a narrow escape. A close call. A reminder, perhaps, but not a sentence. It is days later that the wound turns ugly. At first it seems to be healing. The skin closes unevenly, bruising deepens into purples and greens, swelling subsides just enough to suggest progress. Pain dulls from sharp to sore. Then something shifts. The area becomes hot again. Tenderness returns, sharper this time, localized but deeper. The skin tightens and shines. Fever creeps in at night. What looked like recovery begins to rot from the inside out, and the reason lies not in teeth marks or surface cuts, but in what crushing jaws do beneath the skin. Caiman bites are not clean. They are not designed to slice or puncture and release. Their power comes from force, immense, sudden, and compressive. The jaws close with bone-breaking pressure, flattening whatever they catch. When they release, tissue may appear intact on the surface, while underneath it has been pulverized. Blood vessels collapse. Capillaries rupture. Muscle fibers tear and compact. Fat and connective tissue lose their structure. This is crush trauma, and its danger is delayed by nature. Living tissue depends on blood supply. Oxygen, immune cells, nutrients, all are delivered through vessels that must remain open and functional. When those vessels are smashed, the tissue they serve enters a gray zone. It does not die immediately. It lingers, damaged and starved, unable to mount an effective defense. These are the dead pockets, zones of compromised tissue that look normal at first, but are biologically isolated. They become silent incubators. In the river environment, this is catastrophic. Caiman do not hunt in clean water. They live in systems dense with organic matter, bacteria, and microscopic life adapted to warm, slow-moving currents. Their mouths reflect this environment. Teeth are coated in biofilms built from whatever they have fed on recently: fish, carrion, mammals. When jaws close around a limb, bacteria are not merely introduced at the surface. They are forced deep into tissue, driven along crushed plains where blood flow no longer functions to flush or defend. The immune system responds aggressively at first, sending white blood cells to the area. But without circulation, these cells arrive late or not at all. Antibiotics, if taken later, struggle to penetrate these zones for the same reason. The body walls off the damage instead, encapsulating it in swelling and inflammation. This containment buys time but creates a perfect environment for infection. Warm, moist, oxygen-poor, and rich in broken-down tissue that bacteria feed on readily. The spiral accelerates quietly. Pain increases, not because nerves are regenerating, but because pressure is building inside sealed compartments. Swelling presses against fascia, restricting movement and further reducing circulation. People instinctively immobilize the limb, which feels protective but worsens stagnation. The skin may break down from within, reopening wounds that seemed closed. Drainage begins, cloudy, foul-smelling, alarming. By the time medical help is sought, the infection is no longer superficial. It has claimed territory. Caiman are not monsters in this equation. They are ancient ambush predators shaped by rivers that reward stillness and explosive power. Their senses are tuned for vibration and pressure changes, allowing them to detect prey approaching the water's edge long before it is visible. Their bodies regulate heat by basking and submerging, optimizing muscle performance for short bursts rather than endurance. They do not chase. They wait, often half-submerged, eyes and nostrils breaking the surface like debris. Human encounters follow predictable patterns. Fishing along river margins where footing is unstable and attention is divided between line and water. Pulling nets heavy with catch, leaning forward as weight shifts unpredictably. Slipping on mud banks polished smooth by rising and falling water levels. In these moments, a foot or leg enters the caiman's strike zone, not as prey, but as intrusion. The response is reflexive. A test bite. A clamp meant to secure and reposition, not necessarily to kill. When the person pulls free, the caiman releases. The encounter ends quickly, reinforcing the illusion of escape. What lingers is the damage done by force rather than intent. Ecologically, caiman play a crucial role in maintaining river health. They regulate fish populations, remove weak or diseased animals, and contribute to nutrient cycling through their feeding and waste. Their nests create elevated patches of vegetation that alter flood dynamics and provide habitat for other species. They are not anomalies. They are structural components of the ecosystem. Rivers without them behave differently. Understanding caiman injuries requires understanding time. Unlike venomous stings or sharp bites that declare their severity immediately, crush injuries unfold on a delayed schedule. The danger is invisible at first, masked by intact skin and the relief of survival. This delay is what kills. People underestimate the wound, clean it superficially, and return to activity. The river's bacteria settle in. The damaged tissue cannot resist. By the time warning signs become obvious, intervention is more complex and outcomes less certain. There is a cruel irony here. The caiman's bite is not optimized to infect. It is optimized to hold. Infection is an environmental consequence, not an evolutionary goal. Yet the result is the same. A wound that deteriorates instead of heals. A reminder that survival is not measured in moments, but in trajectories. From a biological standpoint, crush trauma is uniquely dangerous because it subverts the body's usual rules. We are adapted to cuts, burns, and punctures, injuries where damage is localized and circulation remains intact. Crush injuries dismantle this framework. They create hidden failure zones where tissue exists without support, inviting decay. In warm, dirty water systems, these zones are invitations. The human body sends signals early, but they are subtle. A deep ache that does not improve. Swelling that feels firm rather than elastic. skin that grows warmer instead of cooler over time. These are not dramatic symptoms, and they are easily ignored by people accustomed to pain and fatigue in harsh environments. The narrative of survival becomes an obstacle to recognizing danger. Caiman encounters rarely end lives directly. Their true threat lies in what they leave behind, damage that continues working long after jaws have opened. In this sense, the predator disappears, but its influence persists. The river remains inside the wound, carried in bacteria, debris, and compromised tissue. The lesson is not avoidance alone, but respect for aftermath. Any interaction with a large ambush predator near water carries delayed risks that cannot be judged in the first minutes or hours. A wound that looks manageable may already be biologically lost at its center. Recovery depends not just on escaping the jaws, but on recognizing that survival is provisional until healing is complete. The river does not punish recklessness immediately. It waits. And in the case of caiman injuries, it is time, not teeth, that decides how the story ends. Something so small it almost feels insulting to call it an injury. A thin slice across a finger while unhooking a fish. A quick nip at the calf as a line drifts too close to skin. A flash of silver beneath the surface, a flicker of motion, and then the water clouds faintly pink. The cut itself looks clean, almost surgical. No tearing, no mangling, just an opening where skin used to be. And yet it bleeds harder than it should, faster than expected, as if the body has forgotten how to close itself. This is the first misunderstanding people have about piranha injuries, that danger must look dramatic. Piranhas do not crush, shred, or maul in single encounters. Their teeth are not built for that. They are built to slice. Each tooth is triangular, razor-sharp, and interlocking with its neighbors to form a continuous cutting edge. When a piranha bites, it does not saw or worry the flesh. It closes once, cleanly, shearing through skin and superficial tissue with minimal resistance. The result is a wound that looks deceptively neat, but exposes fresh, living tissue instantly. That exposure is the real problem. Human skin is an extraordinary barrier when intact. It keeps microbes out, moisture in, and damage localized. A piranha's bite defeats that barrier in a fraction of a second, creating an opening that bleeds freely because blood vessels are sliced cleanly rather than crushed. Clean cuts bleed more than ragged ones. The vessels remain open, unobstructed by torn tissue, allowing blood to flow until clotting mechanisms catch up. In warm environments, where blood vessels are already dilated to shed heat, that flow can be surprisingly heavy. The river does not wait for clotting. Piranhas live in water that is warm, biologically dense, and rich in suspended life. Every cubic centimeter carries bacteria, fungi, protozoa, and organic debris. When a cut opens in that environment, it is immediately bathed in contamination. This is not unique to piranhas, but their bite creates the perfect entry point. Shallow enough to be dismissed, clean enough to bleed freely, and sudden enough to trigger stress. Stress changes behavior. A person who is bleeding in the water moves differently. Muscles tense. Breathing quickens. Fine motor control degrades. Decisions become reactive rather than deliberate. Hands fumble with hooks, lines, and improvised bandages. People rinse wounds repeatedly in river water, believing dilution equals cleaning. They press and rub, smearing contaminants across exposed tissue. They hurry because bleeding feels urgent even when it is not yet dangerous. In doing so, they often make the wound worse. Piranhas did not evolve to infect humans. Their teeth and feeding behavior are adapted for efficiency in a competitive environment. In many river systems, food availability fluctuates dramatically with seasons. During low water, prey is concentrated, competition is intense, and hesitation means starvation. Piranhas that can remove a mouthful quickly and retreat gain an advantage. The clean slice is not cruelty, it is speed. Their sensory systems reinforce this strategy. Piranhas are acutely sensitive to chemical cues in the water, including the components of blood and stress-related compounds released by injured animals. They also possess a lateral line system that detects vibrations, allowing them to locate struggling prey even in murky conditions. This has fueled exaggerated myths of frenzied attacks, but the reality is more controlled. Piranhas investigate. They test. They remove small pieces. In most cases involving humans, the encounter ends after a single bite because the person withdraws, not because the fish escalate. The escalation happens afterward, in the wound itself. Warm river water slows clot formation. Heat keeps blood vessels dilated. Movement prevents stable clotting. Each time the wound is submerged, forming clots soften and wash away. Bleeding resumes. This cycle can continue for far longer than expected, convincing people that the injury is more severe than it appears and prompting increasingly frantic handling. Stress hormones suppress aspects of immune function, reducing the body's ability to contain microbial invasion in the crucial early window. This is where small cuts become problems. Infections do not require dramatic trauma. They require access and opportunity. A piranha bite provides both. The exposed tissue is fresh, oxygen-rich, and poorly defended until inflammation ramps up. Microbes introduced early can establish themselves before immune cells arrive in sufficient numbers. Once swelling begins, it can trap contaminants beneath the surface, creating localized pockets where bacteria proliferate. The wound may close superficially while remaining infected underneath, only declaring itself days later with redness, pain, and discharge. Human behavior around piranhas increases risk in subtle ways. Fish handling is an obvious scenario. Unhooking fish by hand, gripping them near the mouth, or allowing them to thrash against bare skin brings fingers dangerously close to teeth designed to remove chunks of flesh. Dangling lines near legs while wading creates moving targets that attract investigative bites, especially in turbid water where visual cues are limited. Wading with small pre-existing cuts or abrasions introduces blood and tissue fluid into the water, increasing both attraction and vulnerability. The irony is that piranhas are not the most aggressive fish in these systems. They are cautious, even skittish, compared to many predators. But their teeth leave marks that amplify mistakes. A careless moment becomes an injury that refuses to behave as expected. The danger lies not in being eaten, but in being opened. Ecologically, piranhas play a critical role as recyclers. They remove weakened or injured animals, preventing disease from spreading through fish populations. They strip carcasses quickly, returning nutrients to the system where they support algae, invertebrates, and plant growth. Their presence enforces a harsh rule. Weakness does not linger in the river. This keeps ecosystems dynamic and responsive. In this context, a human bleeding in the water is not prey, but a signal, one that the system is tuned to notice. Understanding piranha injuries requires abandoning the idea that severity is measured by size. A large, ragged wound demands attention. A small, clean cut invites neglect. In tropical rivers, neglect is often more dangerous. The environment does not forgive exposed tissue. It exploits it. There is also a psychological component. People expect pain to scale with danger. Piranha bites can be surprisingly painless at first, registering as sharp pressure rather than agony. Adrenaline masks sensation. Only later does soreness set in, once swelling and inflammation develop. This delay reinforces the tendency to dismiss the injury, to keep working, fishing, or wading. By the time pain becomes prominent, the window for simple intervention has narrowed. The fish itself has already vanished. Piranhas do not linger near disturbances for long. They melt back into shadowed channels and submerged roots, resuming their role as regulators and scavengers. The human remains, dealing with the consequences of a brief interaction that lasted less than a second. In many ways, piranha injuries are the inverse of dramatic predator attacks. They are quiet, clinical, and cumulative. The danger is not spectacle, but process. Clean cuts that bleed, bleeding that invites contamination, stress that degrades judgment, warm water that sustains microbes. Each step is manageable on its own. Together, they create a spiral. The lesson is not fear of the fish, but respect for the environment it inhabits. Hands near mouths carry risk. Open skin in warm water is an invitation. Small wounds deserve immediate, deliberate care, not hurried rinsing and denial. In rivers shaped by heat and life, scale is deceptive. A thin red line on a finger can matter more than a dramatic scar. Piranhas do not need to attack to leave their mark. They only need to remind you how fragile the boundary between body and water really is, and how quickly that boundary can fail when sliced clean. Litter looks empty because it is supposed to. That is the trick. Brown on brown, rot on rot, curled leaves stacked into shallow shadows that appear inert unless disturbed. In the lowland rainforest, the ground is never bare. It is padded with years of decay, a soft surface that absorbs sound and movement. You step over a fallen log, plant a foot where the trail narrows, or place a hand against bark to steady yourself, and nothing in your field of vision suggests danger. Then the ground moves in a way that does not belong to wind or water. The bushmaster does not rise dramatically. There is no coiled display, no prolonged warning posture. The strike is short, heavy and decisive, delivered from a body that was already aligned with the path you took. For an animal that can reach lengths rivaling the largest vipers, it is astonishingly still. It hunts and defends by refusing to announce itself. The first clear sign that something was there at all is impact. Two punctures that feel less like a bite and more like being driven into by a blunt instrument tipped with needles. What follows is not cinematic collapse. There is no instant melting, no immediate loss of consciousness. The danger of a bushmaster bite lies in what begins to unfold beneath the surface, quietly and relentlessly, while the clock starts running. Bushmaster venom is not built for spectacle. It is built for reliability. Large vipers that rely on ambush cannot afford prey that runs far or fights back. Their venom combines components that disrupt blood clotting, damage tissue, and interfere with cardiovascular stability. In prey animals, this leads to rapid immobilization and collapse. In humans, it creates a state of systemic stress, pain, swelling, and internal imbalance that can become life-threatening without timely care. The venom does not need to dissolve flesh dramatically to be lethal. It needs only to overwhelm the body's capacity to compensate. At the bite site, tissue damage begins almost immediately. Enzymes in the venom degrade cell membranes and connective tissue, increasing permeability and encouraging swelling. Blood vessels leak. Surrounding muscle tightens reflexively, trapping venom locally, while the circulatory system carries smaller fractions outward. The limb grows heavy, stiff, and painful. Movement becomes difficult not because of paralysis, but because the body is instinctively protecting itself from further damage. Systemically, the effects are subtler but more dangerous. Blood pressure can drop as vessels dilate and fluids shift into damaged tissue. Clotting mechanisms are disrupted, increasing the risk of internal bleeding even where there is no visible wound. The heart works harder to maintain circulation. Nausea and dizziness appear as early signs of stress rather than poison per se. This is shock in the medical sense, a failure of circulation to meet the body's demands, not the dramatic fainting of popular imagination. The spiral begins with delay. Bushmasters inhabit remote, low-traffic environments, deep forest, old-growth leaf litter, trail edges reclaimed by vegetation. Encounters often happen far from immediate medical help. People hesitate, weighing options, hoping symptoms will stabilize. Myths fill the gap where knowledge should be. Tourniquets are tightened, worsening tissue damage. Incisions are cut, increasing bleeding and infection risk. Venom is sucked or squeezed, actions that accomplish nothing except spreading toxins through damaged tissue and accelerating circulation through movement and stress. Panic compounds everything. People run, stumble, or attempt to self-evacuate at speed. Muscles pump harder. Heart rate climbs. Venom disperses more quickly. Heat and humidity drive dehydration, thickening blood, and straining already stressed systems. Each step feels necessary, but each step pushes the body further from balance. The Bushmaster does not chase. It never needed to. Its strategy is to remain invisible until contact is unavoidable. This snake is exquisitely adapted to leaf litter. Its coloration mirrors decay, mottled browns, rusts and greys that dissolve into the forest floor. Its body is heavy and muscular, capable of explosive force over short distances, but it conserves energy by waiting. Even its sensory priorities reflect this lifestyle. Vibration detection through the ground matters more than vision. Chemical cues guide feeding and reproduction, but defense is triggered by proximity and pressure rather than sight. Thermoregulation plays a quiet role in these encounters. As an ectotherm, the Bushmaster's activity is governed by temperature. It often positions itself where thermal gradients are stable, near logs, under roots, in shaded litter that buffers extremes. These are precisely the places people step when leaving trails or shortcutting through forest. The snake is not drawn to humans. Both are drawn to the same micro-habitats for different reasons. Ecologically, the Bushmaster is a top-level predator with a narrow niche. It feeds on mammals and birds that move along the forest floor, shaping population dynamics in ways that ripple outward. Its presence enforces caution among prey species, influencing movement patterns and habitat use. The forest without it would be noisier, less balanced, and biologically poorer. Its venom, lethal as it is, exists to sustain this role, not to punish intrusion. Understanding the risk of Bushmaster bites means understanding time pressure without panic. The venom does not act instantly, but it does not wait indefinitely either. Early immobilization, hydration, and rapid access to antivenom are critical. Every unnecessary movement costs time and physiological stability. Dehydration thickens blood, exacerbates clotting issues, and impairs kidney function, which is essential for clearing venom components and breakdown products. In hot environments, dehydration arrives quickly, especially under stress. There is also the problem of underestimation. Because symptoms may build gradually, people misjudge severity in the first hour. Pain alone is not a reliable indicator of danger. Some severe envenomations begin with surprisingly manageable discomfort. The absence of immediate collapse is falsely reassuring. Meanwhile, internal processes continue, unseen and unmonitored. Human scenarios repeat with troubling consistency. Stepping over logs without scanning the far side, where snakes rest in the shade. Placing hands on bark or roots to climb slopes, unaware of what lies just beneath the surface. Leaving established trails to save time, trading predictability for speed. These are not reckless behaviors. They are efficient ones in environments that reward efficiency until they do not. The Bushmaster's reputation suffers from exaggeration and understatement in equal measure. It is not a mythical beast that dissolves flesh on contact, but neither is it a snake you can afford to treat casually. Its danger lies in the intersection of potency, invisibility, and isolation. When something goes wrong, it does so far from help, with limited margin for error. The forest does not need to advertise this danger. It relies on camouflage and consequence. Leaf litter remains leaf litter until the moment it isn't. The snake disappears back into stillness the instant its role is complete. What remains is a human body struggling to recalibrate under chemical stress, fighting both venom and its own reactions to it. The lesson here is precision, not fear. Where you step matters. Where you place your hands matters. How you respond matters more than how fast. Myths kill faster than venom by encouraging actions that feel decisive but undermine survival. The Bushmaster does not care about drama. Its venom does not perform. It works steadily and predictably against systems that lose coherence under pressure. In the end, the danger of the Bushmaster is not that it hides in leaf litter. It is that we forget the leaf litter is alive, thermally, chemically, ecologically active. When we move through it without attention, we step into systems older and more refined than our assumptions. The snake's strike lasts a fraction of a second. The outcome depends on everything that follows. The water looks safe because it behaves the way people expect safety to behave. It is shallow, warm, and quiet, barely rippling where the river fans out into a muddy margin or where a canoe noses up to a sandbar. Sunlight reaches the bottom, revealing nothing but pale sediment and drifting fragments of leaves. This is where people step without thinking, where boots sink slightly, where bare feet slide forward, where weight transfers from bank to water in a single casual motion. Then the sand erupts. It is not an explosion so much as a sudden rearrangement of the ground itself. A circular burst of sediment lifts, billows, and collapses in on itself, and in that same instant, something hard drives upward with focused force. There is no warning shape, no silhouette, no time to withdraw. The stingray does not charge or pursue. It reacts, and the reaction is mechanical, precise, and brutally effective. The barb arcs forward, puncturing flesh, then tearing free as the ray vanishes back into the bottom, as if it was never there. The wound feels wrong immediately. Not just painful, but heavy, deep, and contaminated. Unlike a clean cut or a sharp bite, this injury carries the environment inside it. Stingray barbs are serrated, coated in mucus, and capable of punching through muscle with enough force to drag whatever lies on the surface straight into the body. Sand grains, plant fibers, bits of decaying leaf, microorganisms, everything that was resting on the riverbed is now driven inward along the barb's path. When the barb exits, it does not leave a neat channel. The serrations tear tissue on the way out, widening the track and shredding edges that might otherwise seal. This is why the wound is cursed. Not because it is fatal by design, but because it is dirty in the deepest sense of the word. Cleaning it is never straightforward. The puncture collapses inward as swelling begins, trapping debris where it cannot be flushed easily. The body reacts immediately, flooding the area with inflammatory fluid in an attempt to isolate damage and neutralize contaminants. Blood flow increases. Tissue stiffens. Muscles around the injury tighten reflexively, locking the limb into a guarded position. Movement becomes painful, then restricted, then nearly impossible. Stingrays did not evolve to injure humans. Their barbs exist as last resort defenses against predators, large fish, caimans, sharks that attack from above. The tail arches forward instinctively when pressure is applied to the body. This motion is fast, involuntary, and tuned for one outcome, creating space. The venom coating the barb amplifies pain and tissue damage, ensuring the predator releases the ray long enough for escape. Against animals that hunt by grip and bite, this strategy works exceptionally well. In shallow water, however, the same reflex is triggered by feet. Stingrays spend much of their time buried beneath sediment, not hiding but resting. Their flattened bodies and wing-like pectoral fins allow them to settle into sand or mud with minimal effort. As they breathe, water is drawn in through spiracles behind the eyes and expelled through gills on the underside, a system that allows them to remain buried without choking on sediment. From above, they are nearly invisible, just another patch of river bottom, temperature-matched and motionless. Their electroreceptive senses scan constantly, detecting the faint electrical signals of prey and predators alike. A footstep sends a surge of pressure and vibration through the substrate, a clear signal that something large and potentially dangerous is directly overhead. The ray reacts the only way it can. The spiral begins after the strike. Pain radiates outward, sharp at first, then deepening into a hot, pulsing ache that spreads along nerves and muscle groups. The limb swells quickly, sometimes doubling in size within minutes. This swelling is not merely uncomfortable, it is mechanically limiting. Joints stiffen, tendons lose glide. People instinctively avoid moving the injured area, keeping debris trapped where it was driven. In remote environments, this is often followed by well-intentioned but damaging handling, probing the wound, squeezing tissue, attempting to get something out without proper tools or visibility. Each manipulation risks pushing contaminants deeper or widening tissue damage. The serrated nature of the barb means fragments can break off, remaining embedded and invisible beneath swollen skin. Even when no fragments remain, the path left behind is irregular and resistant to drainage. Bacteria thrive in these conditions, protected from oxygen and immune cells by damaged tissue and pooled fluid. Infection becomes a real threat not because the stingray is venomous, but because the wound architecture favors it. Heat and humidity accelerate every stage of this process. Blood flow increases, swelling intensifies, and microbial growth accelerates. Pain discourages weight-bearing, forcing people to shift posture and movement in unstable environments. A person who cannot place a foot properly in shallow water risks slipping, falling, or losing balance while crossing currents or stepping off muddy banks. What began as a single puncture becomes a mobility problem, then a safety problem. Human encounters with stingrays cluster around predictable behaviors. Stepping off muddy riverbanks where visibility is poor and sediment soft. Beaching canoes or small boats in shallow water, jumping out to pull them ashore. Wading across crossings that look placid from above but conceal complex bottom contours. In all these scenarios, feet lead. Pressure is applied suddenly. There is no opportunity for the ray to flee sideways, which it normally would if given space. The defensive strike is not aggressive, it is cornered. Ecologically, stingrays are important engineers of river and coastal systems. Their feeding behavior, routing through sediment for invertebrates, oxygenates the substrate, redistributes nutrients, and shapes the microhabitats used by countless other organisms. Their movements leave trails that influence how water flows across the bottom, subtly altering erosion patterns and sediment composition. They are part of a living landscape that responds dynamically to disturbance. When people enter these spaces, they are stepping into an active system, not an inert one. Understanding the stingray's injury requires understanding this interaction between anatomy, behavior, and environment. The barb is not poisoned in the way people imagine venom. Its true danger lies in mechanics and contamination. It is a delivery system not just for pain, but for whatever the river bottom holds at that moment. The venom intensifies suffering, but the debris defines recovery. The phrase, safe shallow water, persists because danger is usually associated with depth, darkness, or distance from shore. Stingrays invert that logic. They are most dangerous where people feel most relaxed, where shoes come off, where steps are careless, where attention drifts. The ray's camouflage exploits human assumptions as effectively as it deters predators. Both rely on invisibility. Once swelling locks movement, decision-making degrades. Pain narrows focus. People rush exits, choose poor footing, or attempt crossings they would normally avoid. The wound is handled repeatedly, each time with less precision. Contamination remains trapped, not because it cannot be removed, but because the window for proper cleaning closes quickly as tissue responds. By the time help is reached, the injury has already declared its terms. The stingray does not linger. It does not follow. It disappears back into sediment, leaving behind a disturbance that settles within seconds. The water smooths over. The bottom looks calm again. What remains is a wound that carries the memory of that moment inside it. Sand, plant matter, microbes, and torn tissue sealed together under swelling skin. In this way, stingray injuries are not defined by the strike itself, but by what happens afterward. They are environmental wounds, shaped as much by river and behavior as by anatomy. The ray's defense ends instantly. The consequences unfold slowly. The lesson is not fear, but awareness. Shuffling steps instead of stamping. Watching where feet go when leaving boats. Recognizing that shallow water is not empty water. In these ecosystems, danger does not announce itself with movement or sound. Sometimes it waits, perfectly still, until the ground you trust decides otherwise.